Welcome back. This is part 4 of microfilaments. So what we're going to do here is once again take a look at the arrangements in which we find microfilaments in cells. So last time we saw what kind of appeared to be more looser networks of actin, and here we'll take a look at some more organized structures. So some actin containing structures can be really very highly ordered. Actin may be bundled, for example, into tightly organized arrays called focal contacts or focal adhesions, which are involved in anchoring cells to the substrate on which they're growing. And there are a number of actin binding proteins associated with those actin bundles. In microvilli, actin is bundled, and this is possibly the best studied site of actin bundling in cells. So microvilli, just to remind you, are prominent features of intestinal mucosal cells, and their function is to increase the surface area of the cells to improve nutrient absorption. So the core of a microvillus, so over here on the left we have these microvilli. So the core of a microvillus here consists of a tight bundle of microfilaments, and as you can see from the diagram, the plus ends of the microfilaments are extended towards the tip, whereas the negative ends of the microvillus extend down into the cytoplasm of the cell. So the microfilaments are connected to the plasma membrane around the periphery of the microvilli by the motor protein myosin 1 and a protein called calmodulin. And then within the bundle, the microfilaments are held together by proteins such as fibrin and novellin. So this is a highly ordered bundle of microfilaments inside a microvilli. So at the base of the microvillus down here, we can see that the core of bundled microfilaments extends down into the cytoplasm of the cell into a network or web called the terminal web. So the filaments of the terminal web down here are composed mainly of myosin 2 and a protein called spectrin associated with the microfilaments, and they connect the microfilaments to one another and to proteins in the membrane, and in some cases possibly even to intermediate filaments, and we're not going to talk about those quite yet. We'll get to those at the end of this section. So if we take a look at the network or actin that's under the cell membrane, and the best example of this is in red blood cells or erythrocytes, so what we find is that microfilaments are connected to the plasma membrane, and they can exert force on the cell membrane to drive cell movement. So we'll look at this when we look at lamellipodia and filopodia in a moment. So what we have is a network of actin filaments here in red, and then a number of connecting proteins that connect the microfilaments together. But then we have a number of proteins also which indirectly connect the actin filaments to the plasma membrane. So over here on the left, this is a transmission electron micrograph of the inner membrane, the inner leaflet of a red blood cell, and you can see that there are these aggregates of protein here, and that's probably primarily anchorin, which you see over here in the diagram, and then we have these spokes of spectrin which connect the anchorin proteins together, and then associated with the web are also numerous microfilaments. So there is this web of actin that sits just under the plasma membrane, and it can be manipulated by the cell to drive cell movement. In terms of the actin networks which drive cell movement, we often see the actin in those networks forming this dendritic, or this kind of like tree-like structure you can see over here, where the actin filaments are branching off of one another, and so you can see little side branches. So if we have an actin filament and then the plus end is up here towards the periphery of the cell, that would be the growing end. To get a kind of side branch forming, a protein complex called ARP2 and ARP3 binds at a point along a microfilament, and that's facilitated by the WASP family of proteins. So WASP activates ARP2 and ARP3, and that ARP2, ARP3 complex binds to a point on a microfilament and facilitates the nucleation of a side filament from this main filament here, and so the polymerization is towards the cell membrane with the addition of with actin in the ATP bound form facilitated by the protein profilin, which we talked about a little bit before. And so as the plus end, or the barbed end of the microfilament pushes towards the cell membrane, it can actually push the cell membrane out, and this can stimulate and drive cell movement. And then we have other microfilaments which will be capped to stop any further elongation if we want to stop movement. Now, in some cases in the cell, we need very long actin microfilaments, and so in that case, we can regulate the polymerization independently of this ARP2 and ARP3 complex, and that's under the control then of a protein family called the formins. And so the formin will bind to the plus end, the barbed end of a filament, and it's got these little kind of thread-like protein structures that can grab hold of profilin and an actin with ATP bound. And then as the actin gets added, the formin slides along the actin filament, stimulating polymerization. So there are some more ways in which the cell can regulate the networks and the actin-based structures in the cell. I'll be back next time for our last section on microfilaments. I'll see you soon.